Thank you. Well, if Reza takes me as an example, he will be a bad follower of what I teach. I want to start in a different direction. Yani bambaşka öyle bir şey yapacağız. We'll do something completely different. By now, you probably think you've seen every way of constructing Islamic geometric patterns. But I counted 7 different aspects to what I will present. So first I want to be sure there's no more eraser. You have to clear the table. And when the table is cleared, then I have 2 assistants, Humaira and Miriam, and they will present a plate to each table. There are 2 large sets of tables that should get more scissors. Yeah. Tamam, teşekkür ederim. İki makas geçti. So what I would like every table to have is a stack of paper plates, a set of scissors that you can share approximately 1 per 2 people. If there's more people at a table, they'll need more scissors. Some gold foil paper like this, and pencils and tape. And I hope we will get through the entire workshop before 3:30 when the next person will speak briefly, and then we have a wonderful tour to Sheikh Mosque. So what I would like to begin with, even before I go to my slides, is follow through on something that Reza showed us using a completely different technology, methodology than what we've done. If you each take 1 piece of paper, fold it in half, one more desk?
We didn't prepare we prepared 5 desks.
There's 6? Mm-hmm. Okay, they should share it with this. Okay. Let me see, 1, 2, 3, 4, 5, 6. So fold it in half and hold up your paper so I see you fold it in half. This way is a good question. Okay. How can you fold a paper in half? Most people folded it horizontally or vertically, right? Diagonally. Okay, fold it diagonally. Hold up your sheet if it's folded either way. What can you say about the area of the rectangle and the triangle? It's the same. Why is it the same? Same square folded in half. So by division, you know it's the same. So in a sense, it's a visual proof you don't have to measure. So as in Eric Brug's workshop, we're not going to measure. We're going to fold. But the first 2 exercises that I want to show you are the exercises that Reza showed us using a different methodology. Fold this in half as a rectangle. So now you have a vertical or a horizontal and 2 diagonals. And then fold this corner, any corner, to the halfway mark, like that. Okay? Now first let me show you. Well, I'll come back to that. Okay. To the halfway mark. And if you do another corner to the halfway mark, you will get 2 parallel lines. And you begin to see that through paper folding, we arrive at the same geometric results. So first you folded it in half, you have a vertical. Okay, that marks the center point, top and bottom. You take a corner and put it at the midpoint. So you've established a new line, right? Okay, that new line is the line that established the geometry for Reza's initial patterns. The other way of doing it, I'm not going to go back to it, but when he had us fold, not fold, I folded, but cut off one corner of the tile and substituted the gold for the silver. Again, we've established it with much simpler methodology. So my first question that I raise is a hypothesis. And that is, in 750 of our era, the Arab armies conquered Samarkand. That was the furthest eastern extent of the early Islamic Empire. And at that battle, 751 Samarkand, paper technology was introduced from China to the Middle East. Paper technology did not spread a whole lot further quickly, and printing technology only developed hundreds of years later. But paper technology, we know, affected profoundly Islamic culture from the middle of the 8th century on. And I've never seen it written, but I think that playing with paper folding could well have led to the development of some of these geometric patterns. So having showed the two basic geometry steps that Reza showed us, I want to turn now to another aspect of geometry in paper folding. And I want you to take a second piece of paper, either gold or silver, and not yet the slides, fold it in half again, and fold it in half again, and then we will look at the slides. I'm going to go back. So what you notice, sorry, I need this for the translation. What? Yo. This is a square. A square. 1, 1. Okay? Square. This is the simplest, the most basic. But if you notice the name of my workshop, relating number and shape to the nature of space, the number here is what? 1. Bier. Okay. In Arabic, this would be shay, thing, shay'an, thing. In Turkish, adet. Okay, adet, 1, adet. Okay, if we open up what we've done and folded, we have effectively repeated 16 times, but with how many folds? 4 folds. So this is where my work as a textile historian, folding cloth, is very different than the mathematicians. That's not called 4-fold. That would be, maybe 4-fold symmetry, but you could have as many squares as you want. When you have other numbers of folds, mathematicians count differently than I count as a kumashji, right? Textile folder. Okay, so we have 4 by 4, 16 squares. Okay, onota adet, tekrarlandik. Okay, işte. That's what we got. Now, if you look at 1 by 2, how many do you get? 1 by 2? 2. 2 by 2? 4. 3 by 3? 9. 4 by 4, 16. 1, 4, 9, 16. If we did 5 by 5? So we not only have a multiplication model here, but we have squares. If we divide 16 by 4, 4. 9 by 3, 3. So we have squares and square roots. Okay, how many squares am I holding? 1. 1, sorry, with my fingers. Karmakla. Okay, how many squares am I holding? 4. How many squares surround this 1 square? 1, 2, 3. Okay, how many squares surround these 4? And how many squares surround these 9? 7. So 1, 3, 5, 7. We also have a model of odd numbers. Okay, so you begin to see you can add, you can subtract, you can multiply, you can divide, you can square root, and maybe there's more. But you begin to see that you have the entire set of arithmetic operations in this little model. And why did it take me 40 years to figure that out? I should have learned it in elementary school. Did any of you learn that in elementary school, that this is a model? No. Graph paper is a model of the entire arithmetic system. Of Ilm al-Hisab is in here. Now we'll go further and we'll see what al-Khwarizmi did and how he looked at his computations and calculations of al-Hisab as he developed his al-Jabr wa Muqabala, what became algebra. But first I want to build a preliminary to this workshop and say, okay, so far you probably think you've seen all of the ways that geometric patterns can be arrived at. We started off with geometry and the analysis, say, of a square and crossing of 2 squares to create an 8-pointed star. And an 8-pointed star can fit into a square grid, and here you begin to see 1 adet and tekrar lamak, repetition to create an overall pattern, a tiling, a tessellation, a semi-regular tessellation because it has 2 units. Jay Bonner talked about 5 different design methodologies. He talked about using compass and ruler, point joining, polygonal technique, using graph paper, and extending radii. He also talked about an orthogonal grid versus an isometric grid, one based on a square grid and the other based on a triangular grid. Then Eric Brugge did a workshop with compass and ruler work, and he emphasized the square grid versus the triangular or hexagonal grid, which is what Jay Bonner had called orthogonal and isometric. Then Reza introduced in his talk and then in his workshop computer applications and animations, and then modular systems, modular constructions, modular methods. And Selçuk Mulayim introduced transverse systems of lines to create geometric patterns. So we've seen now, 5, 6, 7, 8, 9, 10 methods, and Miroslav Majeski looked at circles and centers, and then I didn't get to add this, but Reza also added cutting and pasting, cutting. So we've seen all these different methods, and now we're going to go to something even more basic. Daha çok basit. You thought you got to the bottom? No, even more basic. So that's, first of all, why we made this grid system, where you see all of the arithmetic systems embedded in one little model. And we're now going to shift to the pennies, American pennies that you have on the table. And the American pennies that you have are designed to replicate the dirhem, or the kurush, that al-Khwarizmi worked with. And al-Khwarizmi worked with all of his algebraic problems in his book on Kitab al-Jabr wa Muqabala are worked out by arranging dirhem. So what I want you to do is focus on arranging these pennies, tight packing these pennies, so that there's no such lines between them, but they're tight packed. And each table has a pile of pennies, share them with one another, and tight pack them. Put them as close together as you can. Share them so each of you has a group of maybe 10 pennies or 12 or 14. And if you work 2 people together, it will extend the pennies a little bit farther. Okay, so everybody has tight packing of pennies. Can you tight pack them? Can you tight pack them more closely so that the space between the pennies is smaller? More close. Daha yakın olsunlar. You see, it takes a mathematician or a crystallographer. No, you should figure out how to make that little hole smaller. Very good. Very good. Now, I want you to look at the dirham, and I admit that I picked dirham from the time of Al-Khwarizmi, silver dirham. And tell me, if you put a center in each dirham, what would you have? What would you arrive at? A square? You get a square if you connect 4 pennies. What if you connect all of the centers? A square grid. A square grid. Now, you've made your pennies tighter packed. What do you now have if you connect the centers? What else? Triangle. So look at the pennies you've arranged tight packed. More tight packed than a square grid. And you see that every 3 centers creates a triangle. But some of you have already visually grasped that there's also hexagons and there's also rhombuses, diamonds. Yeah, equal sides, different angles, opposite, equal angles. Okay, let's move one step further. But first, let me show you from around the time of Khwarizmi. In the 8th or 9th century, there was a series of paintings, palace paintings, found at Afrasiab outside of Bukhara. And just as the coins from his time have a crescent moon and a star, which most of you know is the symbol on the Turkish flag, and often in Muslim countries, the crescent and the star appears at all 4 cardinal points on early Islamic coins. And the same crescent and star is repeated on, in this case, a representation of textile patterns, but in textile patterns that we have preserved that have traveled all over the world. So we have early Islamic textiles in European church treasuries and in Japanese temples. I mean, this just went across the world as luxury silk fabrics. And they often have these star and crescent. So we see the square grid not only in the works of Al-Khwarizmi, but at least with the boar's head flipped in glide reflection, we see a square grid here represented in textiles. So 1 unit repeated covers the plane, in this case, a square grid with 90-degree angles, and you could turn it on the side, and we'll see some other examples. So what is a pattern? A pattern, any pattern, starts with a unit, adet, shay'an, and repetition or iteration. And then you must have an organizing principle. So for the most part, all of the patterns that we have seen in Islamic art have an organizing or principle, symmetry. Symmetry. Okay, what's another organizing pattern? An organizing principle? Usul. Rotation is a symmetry. The 4 basic symmetry operations are reflection, which is mirror, rotation around a circle according to a certain number of degrees, translation, which is moving exactly the same, and glide reflection, which is like walking. So I want a different organizing principle than symmetry. Yes? Flipping is symmetry. Flipping, rotation, glide reflection, and tightness still is playing with symmetry. Did somebody say?
She says, what is glide?
Sliding is symmetry. You're moving along a vector, you're transforming orientation, but you're still maintaining the form, the shape, the shekil, and you come back to a zero, an identity function. What's a different organizing principle?
Radial? No,
Radial is symmetry. Fractal. Okay, we haven't seen. Fractal, you have self-same similarity, but it's with an iteration that reduces or expands. So a tree trunk, a branch, a limb, a twig, a fractal dimension. That's a different organizing principle. What's another organizing principle? Fibonacci numbers. 0, 1, 1, 3, 5, 8, 13, and so forth. That organizes a pine cone, a sunflower, lots and lots in nature. Less in Islamic art, although we have some examples of fractals and Fibonacci numbers. Of course, as I think it was Reza said, Fibonacci, Leonardo Pisano, lived in Algeria, and his father, Imbuja, was a merchant, and he is the person responsible for transferring what in English we still call Arabic numerals to the West in the turn of the 13th century. So the unit is one, adet, bir adet. Repetition, iteration can also be called an algorithm, which is a corruption of Khwarizmi's name from Latin, algoritmus. And the organizing principle we most often see is symmetry. Okay, let's move on and then get back to, let me turn this off for a moment, get back to our exercises. The next that I want to focus on has to do with the paper plates. And I want you each to take one paper plate and a pencil and mark on the paper plate 2 points. Anywhere you want, 2 points. So everybody should have one paper plate. Paper plate, you need the circle. And mark 2 points. I shouldn't say anywhere on it. It has to be on the circumference. 2 points on the circumference. So, for example, you could put 2 points here, mark it with the pencil, or you could put 1 point here and 1 point here, or 1 point here and 1 point here, anywhere you want. So imagine a clock, and you're deciding any time you want. 2 points on the circumference. Okay, then I want you to take your 2 points and fold the plate. Everybody has 2 points marked on the circumference, right at the edge. Kenarda, muhite. Okay, fold your 2 points over so they touch each other. 1 point touches the other point exactly. And fold it, make a crease. Now, can it be that you and everybody around you put your 2 points at exactly the same place? No. What happened?
Everybody has a half of the circle.
Everybody, hold up what you got. Your points are everywhere, right? Your points are everywhere. What happened? And they all do. What happened? Why is it the same? Why is it the same? Because it's a circle is part of the answer. Because it's a circle, why is it the same?
Because the length to the center. For all Because the points are the same from the distance from the center. Yes.
Yes, that's it.
So every perpendicular between any 2 points, every perpendicular, always the same. So I asked you to connect your points and then fold them, connect the points, fold them, connect the points, fold them. Every single perpendicular bisector of the chord gives you a semicircle. Okay, so you are now really playing with the geometry that is inherent in the circle. Daira'nın geometrisi, right? It's exactly the geometry that exists already in the circle, even without us. The participation is, okay, the circle was made for you. Okay. Okay, the next exercise I want you to do goes back to the pennies for a moment. How many pennies can you put around a penny? Who knows? How many pennies fit around a penny? 6. How do you know?
Because that's the standard of the penny we're talking about.
Okay, so how many CDs fit around a CD? 6. How many paper plates fit around a paper plate?
6.
Why?
Because it's the same diameter.
Yeah, so how many of you learned in elementary school? How many of you learned in ilkokul or in preschool that 6 circles fit around a circle? How could it be that we didn't learn this fundamental fact of design of nature and art? Absolutely fundamental. So 6 circles fit around a circle. And let me just see if I have that slide I wanted. Yeah. So what does it have to do with why a hexagonal grid forms when you have circles next to each other or overlapping? In school, this is what we learn is the reason. Because of pi, a Greek letter. Mathematically all over the world, you call it Turkish pi too, p, same thing, Greek letter, right? And what do we learn is pi? 3.1415, etc. You learn numerically. It's just what Miroslav Majeski was saying. We don't learn the visual language. We don't even learn the mathematics. We don't even learn Euclid anymore. We learn the numerical quantification, the basis for calculation. We've lost this profound knowledge and understanding. So at the very least, we might lay it out this way and say, okay, the distance around the circle, pi equals circumference over diameter. That's about as close as children get to understanding why, if you use rubber tires, it's only 6 around a 7th if it's the same diameter, or paper plates, or CDs, or pennies, or kurush, or dirham. It's always invariable. We learned. The circumference ratio of radius to circumference is invariable. But how many people understand what invariable is? Why can you make a design with compass and straight edge this big that can be executed on Suleimania at a monumental scale? It's because of the proportion of radius or diameter to circumference in a circle. This is amazing basic information that we don't know. Okay, Reza made this drawing for me to show that this is a visual proof that 6 circles surround a circle and you connect the centers and it creates a hexagonal grid or a triangular grid if you extend it. This is fundamental. This is in every aspect of Islamic art. Sometimes it's a triangle, sometimes it's a square, sometimes it's a rectangle, but the underlying circles that we've been playing with all week, fundamental. Totally, totally basic. Okay, next exercise takes us in a different direction. I have 45 minutes, is that right? Okay, so I want to, Miriam, could you give me a hand? Everybody should have two pieces of paper. This is a much finer paper. It's advertising because I got it free from a company who gave it to me. And then I cut it. And this is what you need your CDs for. How do we make a circle? Well, so far we've made a circle. Eric Brugge made circles for us. We made it with compasses in Ray's workshop. Now we're going to use a different method, and that is a template. So there may be more coming around. And if there's not enough for two for everybody, somebody should have one. So on the plates of supplies that you got, there should be CDs or lids from yogurt. And here. And I want you to cut two circles. You have scissors and you have pencils. So use the CD or the yogurt lid, which has the same diameter, to draw it. Draw a circle and cut it. If you do two at once, it's approximate, but it's good enough. Then everybody should do one. I have no more. No, because I wanted the translucency. Once you have a circle cut, I want you to fold it in half. And this time, unlike a square, you only have one choice, an infinite choice. Every folding in half will give you a diameter. So it's exercise 1. And then we're going to do 2, fold it in half again. So we're dividing the circle in half. There's 2 halves. We're dividing it in half again. 2 times 2 is 4. We get a quarter or a quadrant. And then we're going to divide it once more. So 2 times, fold 1 in half. Not the other one yet. So 2 times 2, but folding it in half, we're dividing it. So 1 is the circle, adet, divided by 2 equals 1/2, or we're multiplying it, times 2 equals 2, depending on what you're measuring is 1. And then we're dividing it in half again, and then we're dividing it in half again. So how many pieces will we have? Right? Or 8/8 equal 1. Okay, so again, you begin to see the numerical relationship to the iteration of folding in half. Does everybody have it folded in half and in half again? I want to point out that folding it in half and in half again yields only 2 folds, but a 4-fold rotation. This is where the Kumashjilar and the mathematic people have a difference of vocabulary. Yeah. You want to cut it on this line? No, just cut out this part. Okay? Okay, everybody has it folded in half and in half, so you kind of have an ice cream cone. It looks like a flat ice cream cone. Okay, then hold this fixed and fold this radius down on itself. There is only one possible point. If you hold this fixed and fold this radius down on itself, there is only one possible point of intersection. And then the same on the other side. So hold this fixed and fold this down. Does everybody get that, or do you need help? I've never worked with a group that didn't need help. Hold this fixed and fold this on itself. And fold it tight, fold it good. Then hold this fixed and fold this on itself. And give it a good, and then you want to cut here. Yes. Yes, and now the other side. Yes. Open it up and do the same thing on the other intersection of radius and circumference. Let me walk you through this again. This arrow, you hold your finger and hold it fixed. And fold the circumference, the segment, down so that the radius is on itself. So my finger is where the number 4 is. Yes. Hold that straight and put this radius down on itself. And then give it a good crease. Okay, and then hold this fixed and fold this radius down on itself. You have to do it exactly. Yeah, hold it. And then when you open it up, you see this cross, yes, and you cut only to the intersection and out again. Everybody get that? Somebody need help? Okay, so what I want to do, save your 8-pointed star. What I'd like to do at the end of this workshop is something like what Reza did, but we'll do it on the window. And this has 2 purposes, but I want to shift first to another exercise before we get up and move around and lose a little bit of time. And that is that when we folded the gold foil paper and got a square grid, there's something else that we did that I forgot to mention. Anybody want to guess what else did we do besides paper folding and dividing a square? We introduced an element that we haven't played with before.
Triangle. The help of a circle. No. That's it.
A grid, but we've played before with a grid. Diagonal we've played before. What happens? Are each of these squares exactly the same?
Yes.
Look at it. You think they're the same?
They're not, but technically they're supposed to.
Yeah, a mathematician thinks they're supposed to be. But an artist doesn't necessarily think. So how are they different? Why did I choose gold foil paper? They're shiny and they're reflecting light, and each one is reflecting light differently. And boy, did Ottomans play with this in Mother of Pearl. Every single piece in the Mother of Pearl, the Sedef Kari, every single piece is different and reflects light differently. In the case of Mother of Pearl, it's both absorbing and reflecting light. So we've introduced light. So when we put these 8-pointed stars together, later, and the reason it was important for me to get this kind of paper is that we will also be playing with light. And what you will see when we put it together is there's places where the light is translucent coming through and places where the light is completely coming through. So we'll play with that later. But meanwhile, hold your stars, put them aside, take your other circle, and we're going to do the same folding and cutting, but a different algorithm. So think of what we've done as a design algorithm, a series of steps carried out. Everybody did the same series of steps. Everybody got an 8-pointed star. So now we're going to, again, fold your second circle in half, fold it in half again, but the third step is different. So when we're all together, we can do it together. So fold your circle in half, fold it in the half in half. So again, we're doing a half times a half. So we get quarters, but we're not this time doing a third fold. So this time we are also doing a fixed point and a movable point. Can I use your example? And this time, as you see, you're putting your center point here. You're holding this point fixed. And there is only, if this is fixed, there is only one point where the center will intersect the circumference. Everybody see that? You hold this firm, fixed, and move the center point up. So before we were moving the radius onto itself, this time we're moving the center point, not the radius, the center point onto the diameter. And then do the same thing. How can you find this point? And then mark that point. You hold this firm and move this up to where it intersects the diameter. And there is only one place where it intersects the diameter, and then mark that point. So with a pencil, mark that point. So you're holding this fixed and moving that up to only one possible point of intersection so that you've created this line and you mark it. Okay, next step, fold back, open it out to the quarter, to your quadrant, open it out and fold it back to that point, exactly to that point. And then you have a remainder, fold it back the other way. Okay, I've never had an audience that gets this quickly, gets it. It's amazing that we haven't learned this.
Must this point come to this point?
This point is marked here. You fold this radius. You see how you fold this radius where the point is marked, and then fold this back. Yes. Okay, does everybody have the result? Hold up the results. Okay. So hold on to this. We still have 25 minutes. I'm going to use up every minute. Put this aside with your A-pointed star. We'll come back to that. I want to do one more exercise with you. Oh, before I do the next exercise, which is based on the same... Can I have your attention? Before I do the next exercise, it's based on the same geometry inherent in the circle. I want to show you what we did from a perspective of geometry. And again, I thank Reza for preparing this drawing for me. We folded the circle in half. We folded the circle in half again. When in this last exercise, we held this as a fixed point, and we moved the center point to the circumference, this is what we created. So we were not only creating an equilateral triangle, but we were creating a division of the circle that would allow the division to create the six-pointed star. So without a compass, without measuring, without a ruler, we were able to work with the geometry of the circle. The next exercise moves us, using the same geometry, from two-dimensional patterns to three-dimensional patterns. And then I want to break us into three groups to put up the results of our work. So the next exercise needs your paper plate again, or another paper plate. And we want to fold the paper plate in half. And then, let me ask you this. If you have a diameter and you have a paper plate folded in half, how can you find the center? Not by guessing. Fold it again. Fold it again. Exactly. So you can find the center, but don't make a deep fold. Just find the center. And then I want you to fold that paper plate, divide the half circle into thirds. So that's, don't fold it. Keep it in a half circle form. And then from that center point, find out how you can divide it into thirds. So you want all three sections. This is real guesstimate, right? This is too small. You want to adjust it until you really have it all from the center point into thirds. So the result will look something like this. I don't have a diagram of this one yet. Maybe Reza can help me again. Okay, this is what you want. So once you've found the center point, you want to not fold it. You just want to find it and then divide it into thirds, which, because it was in half, we're dividing it into sixths. Okay, so the next step, once you have it divided into thirds, open it out.
How can you divide into thirds?
Well, because you're folding it in half and then dividing it into thirds, you're actually dividing the circle into sixths. Well, you fold it into half and half again. That's going to give you 4 quarters. That's not what we want. We want 6. This is what we want. 6. We want 6, 1, 6 equals 1. So I just wanted that to find the center. Okay, now you want to find from the center how to divide it into thirds.
Oh, okay.
Okay?
Ah, yes, I see it. I see it.
Everybody got that?
Yeah, that's the technique.
It's a technique. Simple technique, very simple. This is real estimation. Okay. Now open your circle up and fold each circumference to the middle of every other line. Let me see how I got that. Wait a second. Fold in half. Fold it into thirds open. Fold to the middle of every other line. Let me figure that out. Okay. Fold to the center, to the middle of every other line. So this is where we're bringing into play point joining that Jay introduced to us, and radial line extensions. You're folding, skipping a radius, folding the next radius to the center, skipping a radius, folding the next radius to the center, and then what do you have? Okay, next step. Open it up, make sure you have your equilateral triangle. Thank you. Okay, now I want you to fold all 3 pieces of the circumference arcs in and fold each point to the opposite side along its altitude. So you're going to do this with each vertex. Okay? You want to do the other 2? To the center. Oh no, to the other side. Each of 3 vertices goes to the opposite of the other side. Okay.
Does it matter if they are like over each other or?
Yeah, okay, so who figured out how to go from 2 dimensions to 3 dimensions and what you need the tape for? And what did you make? What's this shape?
It's a pyramid.
What?
Pyramid.
It's a pyramid, but it's a particular type of pyramid. Tetrahedron. It has 4 faces. That comes from the ancient Greek, from Platonic solids. 4 separate faces, each an equilateral triangle. So use the tape to tape it together, and then we'll break into 3 groups. Do we have 2? Do we have 2? Did you finish? Oh, no, you need 2 more. Okay. Could you get 2 more? Yeah, but we need more. We need more. Okay, now granted, in classical Islamic times, they did not have Scotch tape, but they had flour and water, milled wheat and water, which could be used as glue, right? Okay, so we have 1 die pyramid, pentagonal die pyramid. Do we have another? Who's going to finish the next one? Okay, okay. Okay, so now I want to divide us into 3 groups. And the first group, the challenge is to position these anti-pyramid and fill it in with more tetrahedron. The second group will take all of the 8-pointed stars. And the third group will take all of the 6-pointed stars, and we'll do 3 projects very quickly. We have 10 minutes, maybe 15 minutes maximum. So who would like to work on connecting these with anti-prism? Okay, and who would like to work with the 8-pointed stars? Okay, gather up everybody's table 8-pointed stars. And somebody else gather up from every table 6-pointed stars. Maybe 1 person from each table. 6-pointed stars, 1 person from each table, 8-pointed stars, and 1 person come up and gather the tetrahedra. And what I've put on the screen is the 7 or 8 new ideas that I've introduced in this workshop, working specifically with circles and centers and the relationship of circumference to diameter, diameter to circumference, that we characterize as the Greek letter pi, units and repeats, the use of square grids, which others introduce, light and the reflection of light, paper folding and cutting, and geometric patterns from algorithmic design algorithms. Thank you.